So, problem number 9, to find the electric field at the center of curvature of the arc. So, this arc has radius radius of the arc, and it subtends angle 2 phi at the center of curvature O. We have to find the field at the center of curvature O. 2 phi means it is like this, phi here and phi here, right, and its radius r. Okay, and one more thing is given, it has linear charge density lambda. So, lambda is charge divided by length. Now, let us choose a small length. So, small length we can choose like this, theta, and a small angle d theta with it. So, this length is r d theta. So, this much charge is lambda r d theta, and the field, this makes angle theta. So, this field is how much? It has two components. By the way, these components will be of no use because all these vertical components will cancel. So, this is lambda r d theta k multiplied by, right? So, you write it again, say this is the small field dE in this direction. So, dE is equal to k times lambda r d theta by r square into cos theta. Okay. So, the net field equal to, so integration of that k lambda by r. So, integration of cos theta d theta. Now, the limits of theta, see here, for this line theta is equal to 0, for this line theta equal to minus phi, and here theta equal to plus phi. So, the limits will be from minus phi to plus phi, and it will be k lambda by r sin theta from limits minus phi to plus phi. So, that will be 2k lambda by r sin phi. Okay. So, at the center of curvature of a half circle, semicircle, for semicircle phi will be having value pi by 2, because the total angle subtended at O will be pi or 180 degree. Now, next problem, to find field at center O due to charge on hemispherical shell. Now, it has charge on the surface only. Charge exists on the surface. So, it is equal, so the surface charge density is given as sigma. Okay. Now, so here we will use a result where we have calculated the field on the axis of a ring. Do you remember that field on the axis of a ring? Okay. Let me recall that formula in a previous lecture. We have done so. That's it. See, that is it, right? Due to ring, it is kqx by r square plus x square to the power 3 by 2. Okay. So, we will use this result here. Before that, let us take, divide this shell into rings. For that, I will take an angle theta here and an angle d theta here, small angle d theta. So, this length is equal to r d theta and a ring. See, this will be a ring. This is the ring, right? This. Okay. So, This point O obviously lies on the axis of the ring. Now for that, what is the radius of the ring? Radius of the ring is r cos theta, and the distance x is equal to r sin theta. Now the charge on the ring, charge on ring is equal to sigma times 2 pi r cos theta into r d theta, because this is the area of the ring, the circumference multiplied by this r d theta. This is area of the ring, right? Okay, so here the field will be this way, right? So total field E will be integral of the field due to a ring. Field due to a ring will be much k q, right? It was there k 2 k q x, right? K sigma 2 pi r cos theta r d theta k q x. X means r sin theta divided by radius squared plus x square. That you can write it again, radius square plus x square to the power 3 by 2. Now the limits of integration will be from 0 to pi by 2. So we will continue it in next page also. The field E becomes 2k sigma 2 pi r cube divided by again r cube into cos theta sin theta into cos theta d theta. So we can write d of sin theta, cos theta d theta, right? So this integration is from 0 to pi by 2, theta varies from 0 to pi by 2, or sin theta will vary from 0 to 1. So this is k sigma 2 pi into integral of sin, so it's like integration of z dz, z square by 2, half of sin square theta. So that is half of 1 square minus 0 square. So that is k sigma pi. So k is 1 by 4 pi epsilon naught sigma pi. That is sigma by 4 epsilon naught. You can check it out again. You can check the calculation again. I have to check out whether there is any mistake or not. But the concept is that only. Okay. Now we'll use one more way to find out the field due to hemispherical shell. From there we can check. And this is an easier method, but if you don't know this method, it won't strike you. Normally it won't strike you. Okay, so on the surface consider a small charge dq, and that's it, r. So this field is k dq by r square. Okay, now let's take this angle theta. Then we are interested with this component of the field, right? So that's the sin theta component. So k dq by r square times sin theta, that you can write as k dq by r cube multiplied by r sin theta. Now this r sin theta is nothing but the y coordinate. So k dq by r cube into y. So the total field E equal to summation k by r cube will be there. So integral y dq. Now see the distribution of the charge is like this. So k by r cube. So integration of y dq will be sigma times dA. So sigma will come outside times dA. Okay. Now this by r cube. Now integration of this y dA will be y bar into A. So y bar into A, that means equal to sigma k is 1 by 4 pi epsilon naught sigma by r cube. Y bar means coordinate of the center of mass, that is r by 2 for a hemispherical shell, and A equal to 2 pi r square. Okay, so E equal to sigma by this 2 and 2 will cancel, so 4 epsilon. Okay, so that was also right. Now I think you can guess how we have calculated this y bar. Why we have calculated y bar? Y bar means coordinate of the center of mass. So y bar is equal to how much? Integral y dm divided by m, total mass. Now here so if it is a shell, then the distribution of mass is uniform throughout the surface of the shell. So you can also write integral y dA by A, and this is what we have used. And for a hemisphere, I mean for a hemispherical shell of radius r, the center of mass has coordinate y bar equal to r by 2. Next question, so 11th one. Now here we will find out the field due to a disk. The field on axis of a charged disk having sigma is the uniform surface charge density. Okay, so that is the disk here, charge disk, and this point P lies on the axis of the disk, and the angles are given, the extreme angles are given. I mean this point P, if you draw this line, then this line will make angle phi, right? Now this is the whole charge disk, and this line is on the axis of the disk, right? We have to find out the field at the point P. For that we will use the formula of that ring again. Okay, there it is. So that is y, this is dy. Okay. Now the field due to a ring. Field due to the ring is how much? K Q. Q is how much? 2 pi y circumference multiplied by dy. Let's take this angle as theta, divided by, now this distance will be constant, right? Suppose this distance is A. It was integral k, so kqx, this means A divided by a square plus a square plus radius square to the power 3 by 2. Okay. So the field is integration of the k 2 pi y dy a divided by a square plus y square to the power 3 by 2. Now we can substitute y equal to a tan theta. Therefore dy equal to a sec square theta d theta. Again a square plus y square equal to a square plus a square, so a square sec square theta. Therefore E equal to integration of k 2 pi y. Okay, so in place of y I can write a tan theta dy a sec square theta d theta, again a divided by a cube sec cube theta. Okay, now this will sec square theta, this cube will cancel, so tan theta, this will go outside, 2 pi a cube, right? That will also cancel, a and a cube. So integration of tan theta into cos theta means sin theta times d theta, and the value of theta will be from 0 to 5. Okay. Now replace k by 1 by 4 pi epsilon naught into 2 pi, so that will be minus cos theta, or cos theta, just change the limits from 5 to 0, so that is 1 by 2 epsilon naught. By the way, where has that sigma gone? Sigma, okay, so it's charge, no? Charge is sigma 2 pi y dy. Okay, I should have made the change in this page also. K into charge, right? Sigma 2 pi y dy. Okay, so into 1 minus cos phi, so that is the field, right? So the field due to this disk, point P on the axis of the disk, making angle like this phi. So this is a charge disk, charge density sigma. So here it is the field E will be sigma by 2 epsilon naught 1 minus cos phi. My god, again I missed out sigma. Yes, here sigma here, sigma here, sigma here, and sigma here. Okay, so next is a special case. Next is a special case of this result only. Special case will be like this. Say we have to find out the field due to an infinite plate. Okay. So electric field near infinite plate. Obviously charged plate need not be mentioned also, because without charge you cannot have the field. Okay, so infinite charge plate like this, right? This considered plus charge only, so you have to find field at this point P. Now the infinite charge plate, obviously field will be perpendicular to the plate. For the infinite charge plate you can think it as infinite size disk. It doesn't matter, right? If you are at the mid of this ocean, it hardly matters what the shores, how the shores look like. So it is like the infinite radius disk. So this boundary should not be there, right? I mean, so this phi angle, so this is very very far away. So phi will be how much? Pi by 2. This phi will be pi by 2. So E equal to, then substitute here, cos phi means cos phi will be 0. So sigma by 2 epsilon naught. Right. So near the infinite plate, so infinitely charged plate, then the field is uniform. So between infinitely charged plates also the same thing, uniform field. Suppose you have a charged plate here, here you have plus charged and here you have minus charge. So the charge density on this face is sigma, this is minus sigma. So the field will be how much? It is sigma by 2 epsilon naught due to this, and sigma by 2 epsilon naught due to the upper plate. So it will be sigma by epsilon naught. And what will be the path of the charge? Say if you draw the electric field, it is uniform throughout. So if you release a charge here, say if you release a charge here having a speed v naught, then the path will be a parabola, because see you have uniform electric field here. So the force, you have velocity v naught. So let's suppose this is the x axis, this one is the y axis, so that acceleration in the x axis is 0 and acceleration in the y axis is, suppose the charge is q, so q e naught by m, mass of that particle. So the x coordinate will be v naught t and the y coordinate will be half. I mean at start, suppose the velocity is in this direction only, x axis only, so half ay times t square, right. So you know this, the path will be parabola, and there may be questions whether this will hit the plate, the size of the plate will be given. Okay. Now here the infinite size plate means, that means say if there are two plates, then the gap between the plates is much smaller than the characteristic length or the width of the plate, right. Such that this is the width of the plate, suppose. So this length and breadth of the plate, the gap is much smaller than the length or the breadth. That is the concept of the infinite plate. Okay, now we will recall the shell theorem in gravitation. We have learned before in gravitation the shell theorem, that is, it is the way to find out the field due to uniform shells. Here also uniformly charged shells. So if you have a uniformly charged spherical shell like this, it has radius r and charge q, then if you use the same logic as gravitation, we have done the proof also there. So for the outside points, for outside point here, suppose this point P which is at a distance r. So at P the field is how much? At P field E equal to K Q by R square. For the outside point, the whole shell will act like a point charge here. The point charge located at its center. And for any point inside, say you have a point P dash inside, at a point P dash, the electric field will have value 0. Similarly, at all points inside the shell, the electric field has value 0. Okay. Now let us take the case. Suppose if you draw the graph of field versus this distance from the center of the shell, that is a uniformly charged shell. E. So inside it the field will be 0,